Okay, hello everybody, good afternoon. It's a pleasure to be here at Øredev to talk with you. My name is Edson Yanaga. I'm a director of developer experience at Red Hat. My Twitter handle is @Yanaga. And today I'm going to talk with you about cloud native applications with Kubernetes. You know, Kubernetes was one of the very first projects of the Cloud Native Computing Foundation, and many things have happened since that. So today I'm going to discuss a bit of what has happened in the past few years and how can we solve many of the distributed system problems that we have today using like 2017 technologies. I am also a Java champion and a Microsoft MVP, and I work for Red Hat, which I think that is a very cool combination. And yesterday I gave a talk about the subjects. I also had a book signing at the Riley booth. But just in case you didn't get a copy of the book or would want to know more about this subject of migrating to microservice databases, I just released this book from Riley, and Red Hat developers bought the royalties of the electronic version of the book. So if you just go to this URL, you'll be able to download an electronic copy. And I always like to start my talks with this quote from Forbes. Now, every company is a software company. Just in case you were at my talk yesterday, yes, I always say that. Because I like to say that you don't work for a bank, you work for a software company. You don't work for an industry, you work for a software company. Because software is changing the world that we live. And some people call this digital transformation, digital revolution. I like the definition of digital economy because economy has nothing to do about money, but has everything to do about people. We're just studying how people interact with each other and which are the motivations that people might have to change a system from one state to the other. Some great motivations for people doing that can be power, can be love, can be hate, it can also be money. And I read an article this week talking about how artificial intelligence and how the internet is giving us exponential problems such as fake news. It's hard for us to distinguish what is true and what is false. And the problem is that we are trying to solve problems based from a technology point of view, instead of trying to tackle the motivations that people have for doing that. So I think that we always need to remember that software is made by people, for people. Every time we forget these people components in anything that we do, we can't achieve the optimal results of delivering software into production or in anything else that we do in our lives. But specifically to digital economy, I like to say that the great examples of this economy are that the largest car transportation company in the world owns no cars, which is Uber. The largest lodging company in the world owns no real estate, which is Airbnb. The largest online retailer in the world owns no stock. And the largest content network in the world produces no content, which I believe is very questionable content. But it doesn't matter. The examples are that these companies, they only exist because of software, and the software that they produce is changing the way that people interact with each other. That's what we call digital economy, and that's why I think that we as software developers, we have the most important role in humanity in the next 1,000 years, because absolutely no innovation, no revolution is going to happen for us right now without a software developer behind it. So we can change people's lives for the better, but we can also make people's lives miserable. So we can make a choice. If we want to have that experience of being miserable using software that is not up to our expectations, or we can deliver better software, we can improve people's lives with what we do in our everyday code. I think we can make a choice, and if we're here trying to create better software for people, I think we already made this choice, and I think we can also propagate this message to them, to even more people, so we can help even more people using better software. So some of the reflections that I would like to have today is, first, who is a Java developer here? Majority of you. .NET? A few. JavaScript? Yeah, sorry. And Python? Okay. Ruby? One brave developer there. So, okay. So the discussion here, I think it's mostly specific for Java and .NET applications, because other technologies don't have this kind of issues. One of the common misconceptions that we have these days when discussing microservices is that, for example, for Java, if I create a fat jar, I'm doing microservices, right? So this is a common misconception. Many people adopt frameworks like Spring Boot and Wildfire Swarm, thinking about, well, it's just a great thing to generate a single artifact that I don't have to deploy an application server, which I believe that truly it's a great thing, but it's not a microservice thing because it's a fat jar. You have like many other different requirements. In fact, as a DevOps person, for me, generating a fat jar or a ThinWar or any other kind of artifact is just a matter of artifact choice. So even I believe that when we first heard about this fat jar thing like 5 years ago, I found it simply amazing. But what happened also in the past 5 years was that we created something like called containers. So everybody decided to start using containers, and I think that containers changed a lot the way we think about deployment artifacts. So I truly believe that we're not going to be discussing containers 5 years from now, because containers will have become the default way of packaging applications. So yes, we'll be moving forward. So container is going to be like a dead subject in the next at least 2 years, because we'll have moved to the next step. So, and it changed a lot. So for me, it's much less relevant these days to be discussing fat jar applications compared to ThinWar, because the real deployment artifact these days is a container. Second discussion is that what we so-called Cargocoat is, if it's good for Netflix, it's good for me, right? Because we as software developers in our industry, we tend to just try to copy and replicate the practices that these amazing people are talking at conferences and writing books about that. But many people forget that how many companies in the world have the requirements that a Netflix does or that an Amazon does, and just copying the practices that these people are doing won't guarantee success to our teams, to our software. So we basically have like completely different contexts, and some people just try to replicate that blindly. I always advise people, well, maybe you need to think about what is happening exactly in your team, in your process, which are the challenges that you're having, instead of just applying some methodology or applying some framework or some practice that you believe that will solve a problem that most of us might not even have. So context is king. And to create this context about the discussion that I'm going to have you today, I would like to start with, let's see how technology evolves over time, because it's a very appropriate way for us to start to think about how we ended with these microservices architectures today. So if you look back like in the past 10 years or even 5 years, first, do you still create your own web framework? If we are like Java developers, we know like 15 years ago, everybody was creating your own web framework, and now we ended the discussion, right? We already have proven solutions. Nobody's crafting your own web framework anymore. We created best practices, then we created libraries, then we moved that to services, and we move it on. Now we are solving different kinds of problems. Nobody's discussing the web framework problem anymore. Maybe in the JavaScript world, you're living like in the same moment that we had in the Java world like 15 years ago. You're still creating a lot of things and try to consolidate the best practices in the industry. You'll reach that point eventually, but it might take some time, because we, in different industries, we took our time to consolidate the best practices. So it happens like in with any industry, with any technology that we might want to adopt. In Java, again, do you still create your own ORM framework? People were discussing, you remember Ibetis, JDO, and something like that. Then Hibernate kind of ended the discussion, because we thought, well, and after that, it suffered a lot of changes too. So we kind of consolidated. We know when to apply an ORM framework, when we should not be applying, and which are the best practices when you're using the ORM frameworks. And if you're trying to move our conversation even to a lower level, do you still create your own persistent service? If you look back in the past, like 30 years ago, when people had like problems, we need to persist something into a durable storage mechanism. Well, maybe they had like flat files. They need to create the structure of the data, how to access, how to read the data. Then people realized, well, maybe we need to. They started to create some best practices around that. They consolidate that knowledge as a library. So people started to consume the same libraries. At that time, open source wasn't a thing. So they had to buy different libraries from different providers to try to solve their problems. Then they realized that, well, we can consolidate even further this kind of knowledge. So they created a service. So these days, we don't even think about if we need persistence. We don't create our own persistence framework. We don't buy a library for doing that, or we don't use a library for doing that. We just consume a service, which is usually a relational database service. We deploy or we consume a relational database server, which is providing for a service for persistence. We don't discuss this kind of problem anymore unless you're the person doing creating and maintaining the database server. We just use a server and we assume that data is going to be persisted. We'll be able to query that and move on. So that's how technology evolved in the past 40 years. And this process keeps going on. The same is happening in the microservices discussion that we're going to have today, because as best practices consolidate, you consume services from lower layers of the stack. And this is the traditional path of doing things. You just, first you're still wondering which is the best way to solve the problem. You need to solve that in a very high level layer because it's easier for you to change. You consolidate a bit, you create a library, you consolidate even further, you create a service. And if you can consolidate even more, you might even push that to very low levels of your infrastructure to just consume that as low-level services. So, one of the great examples of this technological revolutions that we had, Netflix started to move from their monolithic architecture in 2009. So the very first versions of their libraries that we know today, they developed that in 2010. But the very first version of their open source libraries were released in 2012. So basically, the concepts that we're using today, and everybody these days admires Netflix, in particular Netflix OSS, because it was a major revolution at the time, and it still is. Because before that, many people weren't aware of concepts like distributed tracing, or circuit breaking, or centralized configuration, this kind of thing. And we have to give a big thank you to Netflix, because they were like pioneers trying to solve these problems. They did a great, they gave us a big benefit in the software development community in general, because they decided to open source the library so anybody could reuse that. In fact, it started on the Java world because Netflix adopted JVM to run their technologies. But you can see I'm digging into other kinds of community too, and it's amazing to see that in the .NET community, in the JavaScript community, etc., you can see libraries like Histrix being created and replicated in their own platforms and languages. I'm pretty sure there must exist, or somebody who's going to create that something similar for Python or for Ruby, and etc. Because we know that this became best practices for solving typical distributed systems problems. So Netflix created that, but they started this journey in 2010, and they released the things that we know today as the Netflix OSS stack in 2012. You know what else is cool from 2012? iPhone 5, right? iPhone 5, I think it's still a great phone, but does anybody desires an iPhone 5 today? We can multiply, okay. But do you want a new iPhone 5 or do you want a new? Okay, so it's better. But do you want, if you wanted a phone today, would you rather get an iPhone 5 or 8 or 10? You see, technology evolved in the past 5 years. You know what else is cool from 2012? Windows Phone 8. This amazing technology. Does anybody has a Windows Phone? No, okay. So you see, a lot of things changes in 5 years. Right? And we're still trying to consume these this technology from 2012 as if it was new. But again, these concepts that we're using from the Netflix OSS stack that were released in 2012, many things changed in the past 5 years, and that's the things that I want to show you right now, because we have newer ways of trying to solve the problems that we first realized that existed 5 years ago. So Distributed systems and of course microservices architecture too, they have a lot of different challenges. I just picked the 5 most popular ones because that's the one that most people are aware of, but have in mind that you have like a huge list of challenges that you need to confront to have a successful microservice architecture. And the most common ones are centralized configuration. Once you have a distributed system, it's very hard for you to know in which state your system is right now. So if we have configuration scattered through like 20 different microservice artifacts, it's very hard for you, like as an architect, to see which is the exactly configuration that we have right now in production. So you need some sort of centralized configuration, so you can check in just a single point, what is the state of my system? I check there, I know how it should behave. Distributed tracing, because in the past you had a monolith, you had a single stack trace, all of the requests goes through the same stack trace, you just open the log or you just debug a single monolith, you know what is happening. But if you have like multiple artifacts and your request is going through different artifacts and different points and ending in a certain result, maybe you have a problem right now. How do you know where is the problem if you can't correlate the request between the services and everything else? So you need some sort of distributed tracing to be able to trace all of the requests from microservice to microservice, and maybe later then aggregate all of the logs and error messages to know, for you to know what is happening in your system. Service discovery. In the past, you only had a single endpoint. Now you have multiple endpoints that might be changing dynamically. And these endpoints, you might have like different versions of your endpoints running your infrastructure at the same time. You need a way to be able to locate that and maybe to filter which exactly endpoint you want, or which version, or something else. So you need this kind of service too. Load balancing. If you have like multiple instances of a given service, maybe you need to load balance the request between the services. If you do that in the dumb way, like a round-robin way, you just plainly doing load balancing. But maybe you need some advanced load balancing features, like I want to route iOS users to that specific deployment because I know that I have a bug with them and I want to monitor them in only that deployment. Or maybe you might have something like client-side load balancing. If you have a geographically distributed system, you might want to do client-side load balancing, because the traditional way for us to think in load balancing is that we have a backend system, we have a load balance in the front, and all of the other server instances, they have the same capacity, and they are all on the same internal networking. So latency is not an issue because everybody has the same latency, everybody has the same throughput and everything else. But if you have a geographically distributed system, depending on which part of the world you are, you might have like different latencies and different throughputs. So the client should be able to choose the best endpoint for it, right? Instead of relying on server knowledge to perform the load balancing. So these are some problems that we have. And circuit breaking, which is definitely the most popular like microservice concept this day, is that, well, now that we have multiple moving parts, I'm not allowed to have like unavailability just because a single endpoint in my system is not working properly. And I used to give this example back in Brazil, which is where I'm from, because in Brazil, when we're watching Netflix, we always watch like foreign titles, like producing in the US or other countries. We always watch the series or movies with subtitles. And and it's a very common thing, or the suggestion, for example. And back in Brazil, like the internet is not that reliable, so we always use it to make fun about that. You were watching a movie or a series, but you just realized that in some scenes, you didn't get the subtitle for that particular scene. So you had to come back on the movie and watch it back again with the proper subtitles. And whenever this kind of thing happened, we thought, well, it was just a problem in my internet connections. That's why I didn't have a subtitle. But could be. But more often than not, when that happened, happens, it's usually also a problem in the Netflix infrastructure, because the subtitle service wasn't available. But instead of stopping the movie and showing you like a blue screen, they just decide, well, Subtitle is not that important. Maybe people wouldn't even realize sometimes that there was a subtitle missing in that scene. So they move the other components of the system. They keep playing while the subtitle service wasn't available. And the same happened to suggestions. If you know the home screen of Netflix, you had a suggestion. I don't know how many of you noticed that, but I think like 6 months ago, there was a specific day. I opened Netflix in my account, and I had some suggestions that I thought, no way Netflix suggesting me this, because I would never watch that. Or else my kids were messing with my account. But then a few hours later, the suggestions came back, and I just realized, well, the recommendation service was down. And they just showed me like a default recommendation instead of like showing me an error. Sorry, Netflix is not, recommendations are not available for you. They just show me a default recommendation, which is exactly what circuit breaking does. You can show a default thing for circuit breaking, or you can have like more advanced strategies, which I will discuss with you later on. So these are the most common problems. And if you think about how Netflix solved that in 2010, Netflix they had like a business problem to solve, so they had business logic, and they just realized that when creating a distributed system, they had all of these problems too. So back in 2012, the way that Netflix had to deal with these problems was everything should be solved on the application layer, because you can quickly fix the things and change the things. We're constantly changing the things because we're still building the knowledge of how can we solve these problems in our architecture. But after some consolidation, 2012, for example, when the very first libraries were created, they were able to consolidate that and use that as a library. 5 years later, we're not in this moment anymore, because most, if not all of these problems, they can be solved by services. And very soon, these kind of problems will be solved by infrastructure. So, and thinking about specific, I'll use circuit breaking as a specific problem, because that's the one that most people are used to. So the way that Netflix uses it, and if you ever use like something like Spring Boot with the circuit breaking Netflix circuit breaking annotations, you know, usually in code, if you have a library, how do you handle circuit breaking? It's a distributed try catch, right? You try to reach a service. If it fails, it gives you an exception, and if you have an exception, you handle that and you answer a default, or you produce some kind of result that can be shown to the user without the user hopefully noticing that something went wrong in your backend. That's how Netflix solved the problem, because that's how systems were deployed 5 years ago. But these days, you need to think, how do you handle your deployments? In the past, we didn't have containers. Netflix used like virtual machines for that. So you had like fewer instances of things. If you work in an enterprise system, maybe usually you still have like only one instance of each one of the services. But as we gradually move to a container world, in a container world, it's not usual for us to have just a single instance of our service running into production. We have multiple, like both for scalability and also for availability. We don't want all of the instances of our services running on the same node, because we have a cluster. We have multiple nodes, and these nodes might be distributed even across different geographical zones. So because we want this reliability and availability thing. So we have multiple instances distributed across that. So typically, the clients that are issuing requests against our backends, they are proxied, and their requests are being forwarded to multiple different backends in different nodes. And if you only had one instance of your service, if that instance is down, you need a default way of answering like, this is not working. But if you have multiple instances going down, think about that. It's very rare for you to have all of the instances of your service going down at the same time. If you're doing that, like you're screwing very badly your deployments, because the traditional way for you to be releasing new versions of your application to production is not just shut down the version and deploy a new one. You're using things like canary releases. So you have like multiple instances. You deploy a new version of your service in a canary deployment. that endpoint is not working properly. All the other ones are still behaving correctly. So this is the mindset that we have today to be solving all of that problems that I've showed before. We assume, just that another example that I'll give you later, Spotify, for example, just admits that we won't release a version of our software into production and all of the instances of the software will fail at the same time. Because we have advanced deployment strategies, we have canaries, we have blue-green deployments and all of these kind of things. So we can assume that at least some instance of my service will be running in production at a given moment. So these days, how can a platform for container orchestration, assuming that we have multiple different instances, can help me these days? And I'm going to show you some things because I work for Red Hat, so like the Kubernetes certified version by Red Hat is OpenShift because Kubernetes is a very low-level abstraction. Is the platform developed jointly by Google and Red Hat. So think about, but Kubernetes is a very low abstraction. Google only wants into Kubernetes the features that is useful for Google. So if you ever try to use Kubernetes, you know it's a very low-level platform. If you want something more developer-friendly, you need a platform on top of that. There are many different platforms running on top of Kubernetes these days. And of course, I have to suggest you to try OpenShift, okay? But what I want to show you today is how can things like a service mesh, which think that a service mesh is a platform that will provide you many different services required for running your distributed applications. And the service that everybody's talking about these days is Istio, which is a platform, an open source platform, supported also by the Cloud Native Computing Foundation, and is being sponsored by Google, IBM, Red Hat, and many other companies. Istio is the platform that is open source platform that is being built by all of these big companies to run on top of Kubernetes, and it can run also on top of other platforms to solve these distributed system problems for you. And these are the cool things that I want to show you today. But before I dig into that, I have to explain some concepts on how Kubernetes and Istio works under the hood so you can understand what's happening. Traditionally, you have an application, you have a container. I use the whale because, well, everybody, most of the day thinks like Docker and a whale and everything else, but I couldn't use the Docker whale because, you know, trademarks. So I use it another kind of whale. So if you think about whale, think about a container. And but Kubernetes doesn't orchestrate containers. Kubernetes orchestrates pods. And when I learned about that, well, Kubernetes orchestrates pods and not containers, I thought, what the hell? Yeah, why did they decide to use pods as an abstraction when the rest of the world, everybody talks about containers? Then you read the definition of what is a pod. A pod is a set of one or more containers, right, that have the same life cycle. But like most of the times, I would say like 99% of the times, your pod has a single container, which makes you think this thing is like, how do I say? I was going to say a bad name, but yeah, it's worthless, right? Because if most of the times you only have one container inside a pod, it's pretty much worthless. But later I realized, I don't know how many of you are like native English speakers or you have like a native-like proficiency of English. For me as a Brazilian, it wasn't that obvious because when I read pod, for me pod meant like a capsule, like when you're packaging something together. But then my manager told me, he's American, he told me, you know what a pod is, right? They're saying, maybe. And he told, you know that in English, pod is the collection of aquatic mammals, right? Like whales. Then everybody started to make sense because a pod is the collective of whales. Then, of course, you had to name that a pod because what is a pod? A collection of one or more whales, or in this case, containers. So that's what we do. Kubernetes orchestrates pods, and important thing to remember, all the containers on the same pod, they run on the same host, they have the same life cycle, and they can communicate with each other using like the localhost interface because they're always on the same node. That's the important things for you to remember. But then again, 2017, to be honest, like people were using that since last year. So 2016 and on, people realized that if you have a pod to orchestrate things, you can have your application bundled inside the pods. One of the containers can be your application, and maybe if you need to add like another functionality in your application without messing with your application source code, you can add additional capabilities in your application just by adding a sidecar container, right? So you're adding capabilities in your application using a sidecar container. Which kind of capabilities? Maybe debugging, maybe tracing, maybe caching, right? You need a cache service, or you need to proxy your request for authorization. An authorization is a cross-cutting concern. Maybe you can, instead of embedding the authentication or authorization logic inside your application, maybe you can add a sidecar container, which will proxy all of the requests to your container, and will apply the authentication and authorization in that endpoint. So you can add it as a proxy, right? Maybe your sidecar container can even act like a monitoring platform, collecting statistics from your application without you having to insert these kind of things in your application source code, right? Maybe if you not only want authorization authentication, maybe you want an HTTP cache, and you don't want to mess your application. You just add a sidecar container that will act as a proxy and a cache, and automatically you had that. You can apply that in Kubernetes. You can apply like sidecar containers. You can say apply these features in all of the containers of type X, and you have all of these applied automatically. But this is the concept of sidecar container. Another concept that I have to tell you is the node proxy. Right? Which is a node proxy? Assuming that you have a node in your system, and that node you have like multiple instances of different applications running that. And the example that I'll give to you, I have like more complete examples, but I'll give you a simpler examples, which is caching. Suppose that you have like 20 different instances of your service inside the same node, and you need to cache specific information from other hosts. If you use a sidecar container, right, all of the pods in your system, like your 20 instances of your pods, will have the same copy of the cache. Then I ask you, is it useful to have like 20 different instances and to have different 20 same copies of the exactly same information? Looks like a waste of memory, right? So some problems are better solved instead of using a sidecar container, are better solved by using a node proxy. So if you assume that all of the pods in your node will have the same information, instead of creating sidecar containers for each instance, you create something that we call a node proxy, which is a container that will run into each one of the nodes. And this node this pod will share the exactly same information in all of the pods that are running on the same host. For example, for caching. Suppose you're caching like the service response from that other endpoint that you're consuming from a third party. You don't want like 20 different instances having the same copy. Like the 20 instances go through this proxy, it caches the information, so everybody's queuing the same exactly information. Okay, that's two different ways of solving this problem. So this concept that we need to have in mind today is sidecar container, which run side by side your application, and node proxy, which is a thing that proxies your entire node in your cluster. So depending on the problem that you want to solve, one is better than the other. Okay, so node proxy, like you can just intercept all of the requests in your remote service, and the red thing here is the node proxy. But enough of talking, I want to demo something for you. So what do I have running here in my machine? I have a Kubernetes cluster called Minikube. So I might have a dashboard. Here I have a beautiful Kubernetes, oops, I have to mirror my screen, of course. I have a beautiful Kubernetes dashboard running here. I have different things going on. What I want to show today is that I deployed a different application, which is a booking sample. It's the classical Istio demo that we have right now. And the thing that I want you to note is that this application is a microservice application. It is a Python front end that's running here. And I have like different backend services running with different technologies. So I think the book details application is running on Ruby, but the book reviews application is Java microservice. So and I have 3 different versions of the Java microservice running here in my application. And I have all of them running in parallel. But I want to add one of the things that Istio can do for me, can do tracing, circuit breaking, and everything else, can do fault injection if you want to debug if you want to know how your system will perform with some problems in production, can do that to you too, but I'll give you the simplest possible example, which is routing. I have here, I want to do a specific routing. I have version 1 of my system, which is running here, but I want to test if the version 2 of my service, of the book review service, will behave correctly. But I don't want to test for everybody. I want to test just with some internal users, like me. So what can I do here? If I sign in the application, let's say, you see that the book reviews, I didn't have any ratings, but now I have some black stars running here. What did I do? I injected a root inside Istio saying that everybody goes to version 1 of my system, but user Yanaga goes to version 2. And if I log out, automatically, yeah, the user information is gone. I'm routing people to default. And how do I achieve that? I just have to open here. If I go here to a YAML file, I just create this kind of configuration inside Istio, and I ask that, well, maybe I want the users, user Yanaga, in this case I'm using a very simple routing mechanism. I'm saying that user Yanaga goes to version 2, but maybe I want to change that. I'm saying that I have version 3 of my service. I want user Yanaga to go to version 3. So I do that, I do Istio ctl replace. And when I do that, I just updated the configuration. If I go back to the service, everybody's using version 1. If I sign in back again, I can see that, well, now I have version 3, which is showing me red stars instead of black stars. So this is the basic, the simplest possible Istio example. But Istio can do very interesting things. For example, it can do circuit breaking, saying that, well, if this node starts to fail, I don't want the request to go to that node. I want that to go to the other instance of the other host. And this particular instance, I want you to take out of the instance pool. That's something other thing that Istio can do. And one of the nice things that I think that I know that Istio can do that is very hard to achieve with other tools is fault injection with delay injection. Because I don't know how many of you are using distributed systems in production. And many people think that the hardest problem in distributed systems is when things go down. No, when things go down, you know that something is down and you know where to chase the problem. The hardest problem in distributed systems is everything seems to be okay, but somehow it's slow. And when the system becomes to be slow, it's very hard for you to identify which point of the system is the cause of this of the slow requests or which is making the whole system collapse. Because we users, we are very kind when the system is slow, right? If you have a web page and it's not loading, what do? You hit reload, right? Because you want to overload even more the backend to make it even slower. So Istio has some features like you can add, well, I want to add a delay of 200 milliseconds between this and this service. And I want that 50% of the request from this endpoint to that point, I want that to fail. So you can simulate using Istio different production scenarios. So you can rehearse before you have like the real scenario into production. So this is one of the things. This is the Istio example I have here. I think I'm over time already, but I want to show here. Here is another example, Istio-based too, but instead of using a sidecar approach, I'm using a node proxy approach. So the default mechanism of Istio is to use a sidecar container called Envoy, which was developed by Lyft and donated to the open source community. This example is using Linkerd, which is another solution usually used as a node proxy. Linkerd was developed by Spotify. So if you use Spotify user. You're using Linkerd in your backend, and Linkerd was also donated by Spotify to the open source community. And Linkerd provides you very interesting circuit breaking capabilities. It has other features too, but I just want to show the circuit breaking capabilities because traditional circuit breaking capabilities gives me different success rate into productions, because the goal for Spotify is not to have 100% availability, because that's almost impossible to achieve. Their goal is 99 something percent of availability. And how do they do that? They have multiple instances of their services running across the globe, and with traditional circuit breaking strategies, how much availability can you achieve? So here I have simulated in this environment, I have 5 different instances of my service, and some of them are randomly, I think in 60% of the times, they are issuing errors. So they are unavailable. So if you don't use something like Istio or Linkerd in your backends, if you have like these instances failing in your backend, the success rate, the overall success rate, the maximum success rate that you can have with this configuration is something like between 95% of the time your request will be successful. Okay, this is the typical thing, and I'm showing these statistics with this beautiful Grafana board. But if you add Linkerd, if you enable Linkerd in your backend, and you use like this circuit breaking strategy, which they call consecutive failures, with these strategies that I have an instance of my service. If I have like 5 consecutive failed requests, I'll remove this instance from my pool, and I'm only forwarding requests to the other endpoints. So that's the basic strategy for that. If I use this strategy, you can check that my success rate is very high. It's like more than 99% most of the time. So this is one of the basic strategies. But you guess, if you're trying to solve circuit breaking in your code, you only have a statistic of the circuit breaking from your instance. If you're using something like Linkerd, you have the overall statistic of your entire system, and you can do some very fancy things like this. You can use Linkerd to use a circuit breaking strategy called success rates. And I'll tell you that for an instance to be considered alive, I need a success rate of 90% of my requests in the last 20 to be successful. If the success rate drops below 90%, I'll remove that node from my pool, and I just forward requests to the other endpoints. And if you can see here, I saw the different rate, right? With consecutive failures, the overall success rate, something like, if I get the average, should be 95. Here I have like 90, yeah, it's between 94 and 96, like 95 most of the time. Here you can reach like 100%, but on average, it's something between 96 and 98%. But if I use this advanced circuit breaking strategy, I can reach like almost 100%, but on average it's like more than 90% most of the time, because now you have like the overall system statistics to be using these advanced circuit breaking strategies. Okay, and that's some of the features that I wanted to show you today. Of course, all of these, if you want to know more about Istio, about Linkerd, about this, how to solve this kind of distributed system problems using infrastructure instead of application code, you can join you can find all of this information on the developers.redhat.com website, because we blog a lot about that. We have some very sharp engineers working on top of the solution too. I would love your feedback, and just in case you have any doubts, you can also ping me on my Twitter handle @Yanaga. And thank you very much. Thank you.